Hi everyone, I am Madam Musmaya. In this video, we are going to discuss on pressure of a gas and RMS speed of molecules. Here, pressure of a gas. So can imagine how a gas molecules move randomly from the kinetic theory of gases we discussed before in the previous lesson. Okay, so the gas move randomly in a container. Yeah, you can imagine. So we divide their motion into three direction. Okay, along X, along Y, and along Z. Okay, and we assume also the gas is in the container, cubic container. Okay, a very large cubic container. So let's say the length of the container, okay, the cubic container is L. Okay, so all of the sides have length L because this is a cubic. And let's say also the number of molecules inside here is N, okay, capital letter N. And then mass of a molecule is equals to M. Okay? So one molecule has mass M. And the velocity of the molecule is C. Okay. Some books use V, but we refer to our book as a textbook, our Oxford Fajar book. So we use C. Easier for you to refer. But other books sometimes use V. Okay, so from the origin here, let's say this is the starting motion of the molecule. So it will move along X with velocity U. So the velocity generally is C. So for the component of the velocity, we can write as U, V and W. V and W. So this is the component of velocity of the molecule of a gas along X. Okay, U along Y, V, and along Z, W. Okay, component of velocity, U, V, W. And then we are going to relate with the momentum, and momentum is mass times velocity. So we have mass here, M, and velocity, U, V, W. So we refer to the motion along X first, along OX. So we use U, the velocity used is U. So the change in momentum will be moment mu minus negative mu. Okay, because the momentum, initial momentum minus final momentum. So let's say direction is this way. So mass time u for towards x, and then oppositely negative u, so becomes negative mu. So the change in momentum along x will be 2 mu. Okay, so we take the magnitude 2 mu because it's actually the motion is everywhere, any direction. So we just choose these three component only. Okay, so we take the magnitude 2 mu. Okay, so you can imagine like this lah. I repeat the animation. Okay, then collide with the wall, and then going back, opposite direction. So the momentum will be 2 mu. And then time taken. Why we need time? Because we are going to relate with pressure. Okay, pressure is force per area. So the force is rate of change of momentum. Okay, so rate of change of momentum, there are relationship with change in momentum. Okay, the momentum with the time to get the force, rate of change of momentum. So we need to get the time also. So from the formula of time, distance divided by velocity. So distance traveled by the molecule here is L, and then another L, 2L, right? 2L divided by U, right? The velocity is U. Okay, okay, next. Now we are going to relate with the force. Okay, force is rate of change of momentum. So therefore, we substitute the change in momentum to mu, and the time taken is 2L per U. Okay, these two we substitute into the rate of change of momentum, and simplify the this one, we get mu squared per L. Okay, cancel out 2. Okay, bring up u, so we get u squared m per L. So this is rate of change of momentum, and this is also the force. Okay, because force is rate of change of momentum from the Newton's second law. Okay, Newton's second law. So this is force. Okay, now we are going to relate with pressure. And before that, for the total force, this is along u, along x direction. So we use u. So the total of force along x, okay, there are many molecules, n molecules, okay. So we have maybe we have u1 squared, u2 squared, and un squared. So combine all will give you the total force. Okay, it will give you a total force. Okay, next. Now we are going to combine, relate with pressure. So pressure is force per area. So this is the total force. So you substitute into here, and the area is one side of the cubic just now, one surface of the cubic. So the surface of the cubic is a square. Okay, so L times L is L squared. Okay, so this is area of one of the surface of the cubic just now, where the collision happened. The molecules collide with the wall and then bounce back. So this is pressure. Okay, haven't finished. Because we are going to simplify this. Okay, so L here bring down, or this one bring up, become 1 per L2. So we get L cube. Okay, M per L cube. Okay, then continue from here. Definition for the mean square speed along OX is given by this one. Okay, this is the symbol used for mean square speed. Okay, mean square speed along X only, so we use U. Along X, so we equal mean square speed, okay, is equals to u1 squared plus u2 squared plus dot dot dot, okay, un squared divided by n, because the mean, mean. So this is the square speed. So the mean by this, using this symbol, so the mean means divided by n. Okay, this is the definition for mean square speed. Okay, so you are going to relate with the pressure. Okay, so we cross multiply here n mean square speed. So we substitute into this expression. Okay, this one is this one, right? So we cross multiply, so we get n mean square speed. So we substitute into here. So the equations for pressure now becomes m per L cube, n, then mean square speed. Okay, any problem or not for this one? No,
Teacher, can you go back about mean square speed?
Mean square speed, this is the definition for mean square speed. Square speed because u squared. Here the speed is square, right? So that's why square speed. And then the mean here, so we use this symbol. The mean means all the square speed for u1, u2, u dot 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 un. So divided by the total of molecules, number of molecules. So we get the mean. Okay, then we cross multiply.
Okay.
So we cross multiply here. So we substitute into here. Okay, so this may be new to you all, the mean square speed. Okay, so now we continue. So we just rearrange the equation here. Nicer to look at, right, like this. So nm per L cube, same thing actually. We just rearrange. So nm mean square speed divided by L cube. Okay, then continue from here. Continue from the pressure here. So this is the general equation for pressure. So we are going to be more specific, okay, more specific with the pressure here. This is along x only, okay, along x. We have along y, we have along y and along z, okay. So we are going to be more specific now. Okay, ready. So the mean square speed for generally is C, where in the previous first slide, I show you C is the velocity of one molecule, and we have the component U, V, W for along X, Y, and Z. So we total this up becomes the mean square speed of the molecules of the gas. Okay, so it's a mean square speed along x plus mean square speed along y plus mean square speed along z. Okay, along x, y, z. And they all have equals value. Okay, they all have equals value. Because there are so many molecules, many molecules, and they move randomly and everywhere, actually every direction. So for the component we just choose along x, y, and z, and actually they are all the same. Okay, they distributed uniformly, the whole actually not distributed lah, they move randomly, randomly. Okay, the keyword is randomly. So they all have the same value. Okay, the reason again, n is very large and the molecule moves randomly. So therefore, they are all equals in value. So therefore, they becomes 1/3 of mean square speed, C. Okay, general value of speed of molecule C. Okay. So this one plus this one plus this one. So 1 plus 1 plus 1 is 3. So we bring to the right side becomes 1/3. Okay, 1/3. So you can substitute any of this. Let's say you equate this V as U. So this is mean square speed U. Okay, this one also U, this one also U. So becomes 3. 1 plus 1 plus 1, for example, 3. So bring to the right side becomes 1.3. Okay, mean square speed. Okay, now we cross multiply, just choose one, U. So actually it's 3 mean square speed for the U means the speed along X direction. Okay, understand or not the mathematical part here? Okay, the mathematical part here where where they are all have the same magnitude, right? So that means becomes 3 mean square speed along X. Okay, 3. In other words, you imagine this one is U, this one also U lah, because they all have same magnitude. So this one U, this one U. So we have 3 mean square speed along X. Okay, any problem? The mathematical part here. No, Okay, so now we substitute into here. So we substitute into here, the mean square speed along X become mean square speed. General we use C per 3. 1/3 lah, 1/3. Okay, next. We cross multiply L cube to the left side become pressure P L cube. Okay, next. L cube is volume because it's a cube, right? Cube shape, the shape of the container we imagine just now as a cube. So L times L times L cube is a volume actually. So we write here volume V, capital letter V. Okay, next we bring to the right side becomes Nm per V. Okay, now Nm per V is density. Okay, we have N molecules times M. Remember that M is for mass for one molecule. So Nm means the whole molecule. So divided by the volume, so we get the density of the gas. Okay, so Nm per V represent the density of the gas. So this is one equation for the pressure of the gas. Equation 1 can consider as equation 1. Another one we can write as number density. Okay, number of molecules density. Number of molecules per volume is n, small letter, number of molecules density. Okay, we can write like this. This is not number of moles, so we use same symbol as number of moles. So common mistakes every year students make, they will confuse this letter n as a number of moles. So I remind you all again, this is not n number of moles, but this n represent number of molecules density. Okay, so n is equals to number of molecules per volume. Okay, so this is two equations. Okay, two equations to be memorized. Besides the first one lah, from the first one we get another two. Okay, memorize all this. So in your books, our textbook got all this. The derivation for this equation for pressure of a gas is in your book, so you can refer to your books and also refer to my PowerPoint notes. I give later. Okay, so this is another formula to be memorized. This is the first one lesson on a previous lesson. Okay, this is from previous lesson, and we add another one. Okay, another 3 set. Previous lesson 4 set. This is another 3 set to be memorized. Okay. So any question before we do example? Okay, I show you example, then you can do the checkpoint. Okay, no problem, Okay, so the first example. Okay, we read first the question. The mass of gas in cylinder of volume 0.050 meter cube is 0.062 kilogram. So the pressure of the gas is 1.5 times 10 to the power of 5 Pascal. So estimate the RMS speed of the gas molecules. So we are going to estimate the RMS speed. So the solution is, okay, you are given, determine what are given in the question. So the information given is V, volume, and then mass, 0.062 kilogram, and the pressure 1.5 times 10 to the power of 5 Pascal. Okay, all SI unit already. So we are going to find the RMS speed. Okay, CRMS. So from the formula just now, okay, which one is to be used? Okay, from these 3 equations, which one is to be used? So n not given, a number of molecules we don't know. Okay, and the number of density, molecules density also cannot be used. So the one that can be used is 1/3 rho mean square speed. Okay, density. So we use this one. Okay, next. And density can be calculated using mass per volume. And this mass is mass for the whole molecules, whole molecules. Okay, mass for the whole molecules. So we substitute into here. Okay. Oh. Okay. Next, we rearrange the equation because we are going to determine the mean square speed first. So we determine the mean square speed before we determine the square, the RMS speed. Okay, so we determine the mean square speed first. Okay, rearrange the equation here. We get this 3V pressure P per M. Okay, so mean square speed, RMS speed is equals to the mean square root of mean square speed. Do you understand what is meant by RMS or not? RMS is root mean square. This is square root. Square root. So root mean square is the square root of the mean square speed. Okay, so root mean square. So you put the root square root here. So square root of the mean square speed. We give you the RMS speed. So short form we say RMS. Okay, short form for RMS, I repeat, is root mean square. Okay, root mean square. So that's why you put the square root here to get the root mean square. So we substitute the mean square speed into here. This is square speed. So square root of this, you get root mean square speed. Understand? Any problem before we substitute the values? Any problem here? No, Okay, now we substitute the value of volume and the pressure and the mass, the mass of the gas. So this mass, I repeat again before you confuse. This mass is mass of the whole gas. And in the equation here, okay, the three equation here, this mass is mass of one molecule. Okay, this mass is mass of one molecule. So don't confuse with these two mass. Okay, don't confuse with these two mass. I repeat again, okay? This mass is mass of the gas, okay? Mass of the gas. And in the equation, as we derived before, this mass is not mass of the gas. This is mass for one molecule, okay? Mass for one molecule. That's why we have a big letter N here, okay? Big letter N here. So big letter N here times the mass of one molecule will give you the mass of the whole molecule. So be careful with the symbol use. So in this chapter got many similar symbol used, but actually slightly different definition. So must be very, very, very careful. Okay, any problem? Oh, we haven't come to the final answer yet. So the answer is 600 meter per second. So the root mean square speed of the gas is 600 meter per second. Okay, we will go in detail in the next subtopic for the root mean square speed. Okay, got special topic. So this is the introduction to you all for the root mean square speed, how we can get it from the mean square speed. In other words, the relationship between root mean square speed with the mean square speed. So this is the relationship. Okay, now you can do the checkpoint 9.2 already. So it's a very short subtopic. So you can do 9.2. Even though it is short but complicated also to understand. And because we have touch this topic, RMS speed, sorry, twisted tongue. So we go to the next subtopic, RMS speed of molecules. Okay, ready? Okay, RMS speed of molecules. Okay, from the previous discussion, this is the relationship between RMS speed with the mean square speed. Okay, continue from here. So the this is for one molecule, okay? For many molecules, so C1 squared plus C2 squared plus dot plus Cn squared divided by n. Okay, don't forget square root. Okay, then this one can be derived into square root of 3 kT per m. So this is the RMS speed for the molecules. Okay, square root of 3 kT per m. So how we get this equation? Okay, so we are going to derive it. Continue from the pressure of a gas just now. Okay, continue from the pressure of a gas. So we choose one equation. One equation. So remember these three. Okay, so we choose one. We choose the third one. Cross multiply become PV. Okay, PV, cross multiply become PV. So we choose the third equation. Okay, so cross multiply PV. So PV equals to N, capital letter, N, M, mean square speed per tree. Okay, understand where this come from? From the previous discussion. Okay, from the three equation of pressure, we choose one and then we get just cross multiply V. And then from the previous lesson, we use PV equals to NKT. Okay, go back. So from this the previous lesson, we choose one of the equation here, PV equals to NKT. So if you have done the revision, then maybe easier for you. So I go back to straight away from these two formulas we memorize. Okay, so we take one, PV equals to NKT. Okay, so now we equate these two. Okay, equate these two and cancel out N. Okay, cross multiply 3KT. M also cross multiply. And then for RMS, we square root this one. Square root, we get RMS speed. Okay, we get RMS speed. So proven, the formula is proven. Okay, the formula is proven. Okay, any problem?
Teacher, we can
Yeah.
choose any of the three formula or must use this?
Yes, can choose any three.
Or any? Okay.
So one of the RMS is equation is this one, square root of 3KT per M. So can choose anyone to prove this. Okay, so I show you one.
Okay,
So I
teacher.
show, okay. Okay, next, as you, I don't know who just now, I cannot recognize your voice. May I know who?
Ramesh, teacher.
Okay. So now we try another one. As you mentioned, actually I'm going to discuss. So another equation for the RMS speed is square root of 3 RT per capital letter M. This M is a molar mass. So we choose another one. We choose, let's say we choose pressure 1 per 3 densities mean square speed. And from the previous lesson, we choose PV equals to M RT per M. So we check again the equation, these two equations, which one we choose. So we choose this one, and we are going to equate it with this one. PV equals to M per molar mass RT. Now we choose these two. Okay, choose these two. So we will get this one. Okay, ready for the derivation of this equation. Okay, so we equate this, okay, or we substitute this P into here, okay? So no P here, right? So we substitute this P into here, so we get this one. Okay, it's just mathematics, so you can do. Then and don't forget the rho is M per volume, okay, M per volume. So the volume also no longer here, right? So we cancel out the volume. Okay, the P also cancel because we substitute into here. And the volume also cancel because density here is referred to the NM. So we can cancel the N also, number of molecules. Okay, so now we get this. Okay, we cancel the M. Okay, we get 3 RT per M. We cross multiply, 3. So the mean square speed is this one. So therefore, RMS speed, we put a square root to this term, TR3 per M. So we get this one. Proven the second formula. Okay. We have the third one, but later. That one, I want you all to do by yourself. So later, so I give you these two only. Okay, it's very easy to memorize because RMS speed is equals to square root of 3 kT per m. Another one is 3 RT per molar mass m. So this one is mass for one molecule and this is a molar mass. Okay, molar mass. And then the K is a Boltzmann constant. If you cannot forgot already what is meant by K. K is a Boltzmann constant and R is the gas constant. Okay, 8.31. Boltzmann constant is 1.38 times 10 to the power of 23 or negative 23. Not, I forgot already. So you can refer later, the Boltzmann constant. Okay, so another equation to be memorized, and also don't forget how to derive it, because can be the question for derivation can come out in the essay question, so must be very, very careful. Okay, then we try question. We try a question for the RMS speed. Okay, calculate the root mean square speed in meter per second of argon atoms at 27 degrees. Okay, we try this question. Okay, from these two, you can choose either one. Okay, it's up to you. Okay, let's say we choose square root of 3RT per m. Okay, we choose this one. So we just substitute the values of R, 8.31 or 8.314. Then the temperature here, 27. Don't forget to convert to Kelvin, so plus 273. But the problem is we don't know molar mass. Okay, so we don't know molar mass. So you need to refer to the periodic table. Okay, periodic table for argon. Okay, this is argon, argon. So you refer to the periodic table argon here. So the value is 39.948. Okay, gram per mole. The given in the periodic table is in gram per mole. So you need to convert to SI unit, kilogram per mole. And this one is for 1 mole. So 0 convert to kilogram per mole. Okay, because this is already molar, this is a molar, sorry, it's a molar. So molar mass, so you substitute into here straight away 0.03995. So the answer is 433 meter per second. Okay, easy, right? The harder part maybe the derivation, derivation. Okay, so you can also use 3 kT per m, 3 kT per m. But the m here, remember, the m here, the m for the first formula is the mass for one molecule, not the molar mass. Okay, so you must convert the molar mass to the mass of a molecule. This one is for mole. Molar, molar means per mole. So must be very careful. Okay, we try one more. Uranium has two common isotopes. Okay, so with the atomic mass of 238 and 235. So the atomic mass of the uranium. So one way to separate these isotopes is to combine the uranium with fluorine to make uranium hexafluoride gas. Okay, so UF6. A little bit chemistry here. Okay, then exploit the difference in the average thermal speeds of molecules containing the different isotopes. So we are going to calculate the RMS speed for each type of molecules at room temperature. Okay, so we do for uranium 235 first. Okay, then uranium 238. So from this equation, just now we choose 3RT, square root of 3RT per m. So next we choose square root of 3 KT per m. Okay, you can choose this one also actually. But purposely for this example, we choose square root of 3 KT per m. Okay, and remember again, this is m, mass for one molecule. This big letter, capital letter M is for molar mass. Okay, I repeat many times already. Okay, so we do for uranium 235. Okay, for uranium 235, okay, so the total of gram per mole, because 235 is gram per mole, 235 is gram per mole. So 235 plus 6 times 19 equals 2349 gram per mole. So again, you refer to the periodic table. So fluorine is 19, okay, and uranium is 235. So you total all the mass per mole. Okay, refer to the periodic table. Periodic table, I repeat, the periodic table given is the mass per mole. Okay. So To convert to the per molecule, so you use Avogadro number. Okay? So you use Avogadro number. So the periodic table, we get the 349, the total, the molar mass, okay, gram per mole, 349 times 10 to the power of negative 3. You get the gram here already convert to kilogram. Then Avogadro number is 6.02 times 10 to the power of 23. Okay, 23 for one molecule. So we get 5.79 times 10 to the power of negative 25 kilogram per molecule. Okay. So any problem? No, eh? So we use the relations. Actually, this one comes from the relationship N per NA equals to M per capital letter M. Okay. So you from there you get this one. And you've learned also this in chemistry, right? Okay, so you get 5.79 times 10 to the power of 25 to the power of negative 25 kilogram per molecule. Okay, now we can substitute all this value into the RMS speed equation. Okay, RMS speed equation. So 3 times Boltzmann constant is 1.38 times 10 to the power of negative 23. And then the absolute temperature, 27 plus 273 Kelvin. So not mentioned here, but mentioned as room temperature. Okay? So room temperature is 27 degrees Celsius. So convert to Kelvin. Okay? So not mentioned room temperature means it is understood 27 degrees Celsius. Okay, then divided by the mass of a molecule. Okay, so 5.79 times 10 to the power of negative 25. So the answer is 146.461 meter per second. Okay, we write until 3 decimal place here because the mass is very, 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 very small. And we are going to compare with the uranium-238 later. So that's why we write here 3 significant, 3 decimal places. We write in 3 decimal places. Okay, so we do the same for uranium-238. So this is the periodic table just now. Fluorine, 18.998. I write as 19 just now. Okay, we do the same for 238. You will get 145.833. Okay, 145.833. So I didn't what? Show again the step. Just the same, use the same step to get RMS speed for the uranium-238. We get 145.833. Okay, so we can compare these two velocity RMS speed. This RMS speed. So one of the use of RMS velocity is to predict how fast molecules are moving at a given temperature. So between uranium-238 and uranium-235, so we can compare which one is the faster. Okay, so this is one of the use of RMS velocity. So you will learn in detail when you further your study. Okay. So from these two values of RMS speed for U3235 and 238, so that means the uranium-235 is faster than uranium-238. Okay, any problem with this question? No, Okay, so now we still got time, so I want you all to derive one more, okay? One more equation for RMS speed. So these two done already. So the third equation is square root of 3 P per rho, right? So this P is pressure lah. Okay? In the previous slide, we use a small letter, so you can use small letter. So 3 P per rho is the density. So you can do this. And also now I add another one formula for the equation for RMS. Okay, that's all for my video. Thank you for watching. So please subscribe to my YouTube channel if you don't want to miss any of my video.